Let us go for one more set of problems on motion in 1 and 2 dimensions from competitive examination papers, and I wish to include a couple of problems from motion in a straight line and motion of a swimmer in a flowing river. So here is the first problem coming, and this is telling that the velocity of a particle moving in the positive x direction varies as v is equal to k into root over of x, where k is a positive constant and x is the position coordinate of the particle. Assuming v is equal to 0 at t is equal to 0, find in part A velocity and acceleration of the particle as functions of time, and in part B average velocity over displacement s from the starting point. So this is an example of straight line motion, and since they have said that velocity is a function of position coordinate as v is equal to k into root over of x, squaring both sides we might write down v square is equal to k square into x. Differentiating both sides with respect to time, we might write down that d dt of v square is equal to d dt of k square into x. In my next step, as you can see, it's a function of velocity. I can't differentiate straight away. So applying chain rule, I'm writing left hand side as d dv of v square into dv dt. That is left hand side. Right hand side, k square is a constant coming outside, and this is dx dt. In my next step, well, differentiation of v square with respect to v becoming twice v. So left hand side becomes twice v into dv dt, and right hand side, if you see, is k square, but dx dt, the rate of change in position in time, that is called velocity only. Therefore, right hand side can be expressed to be k square into v. And then again, I can see from both sides v cancelling out, because in general velocity is not 0, and therefore I am getting here that twice dv dt is equal to k square. In the next step, we separate the variables. Here are two variables, velocity and time, and separating variables I might write down dv is equal to k square by 2 into dt. Integrating both sides now in the next step, integration of dv k square by 2 is a constant kept outside integration of dt. They have told you in the question at the very beginning, at time t is equal to 0, velocity was 0. So these become the lower limits of time and velocity respectively. So I put the lower limits. Of time it is 0, of velocity it is also 0. Upper limit, let the times upper limit be time t, and for velocity that is coming out to be v. I am expressing v now as a function of time. That's my intention. Integration gives left hand side is becoming v minus 0, right hand side k square by 2, and then again t minus 0. And we have got v is equal to half into k square into t. That is the first part of the question. We have expressed velocity of the particle as function of time, which is v is equal to half into k square into t. And once we get velocity, let us go for acceleration next. Acceleration, as you are aware, is given by derivative of velocity with respect to time, dv dt. So this is d dt of v. This was half k square into t. Half k square is a constant coming outside, and differentiation of t with respect to t is only 1. So this is this only, and I'm getting acceleration is a constant given by half into k square. That is my second result. We have got both the parts of part A of the question. Velocity is varying linearly with time given by v is equal to half k square into t, and acceleration of the particle is a constant given by half into k square. These are the answers of part A of this question. The question also has got a second part B. Let us go for that next. Moving on to part B of the question, they want us to find out the average velocity over displacement s from the starting point. And you remember, average velocity over a trip is equal to the total displacement by total time of travel. So, let us get back to the result number 1. We have got earlier that equation number 1, that was velocity is equal to half into k square into t. And since v can be expressed to be derivative of x coordinate with respect to time dx dt is equal to, we have said earlier, we might write down this is dx dt, rate of change in position with time, that is velocity only, and that is equal to half into k square into t. Separating the variables once again, here you have got two variables. One is the x, position coordinate of the particle moving in the x-axis. Other variable is time t. So therefore, I keep dx on the left hand side and take dt on the other side, that is half into k square into t into dt. Let us go for integration next. Integration of dx, right hand side, half k square is a constant, integration of t dt. At the beginning of the trip, time was 0, that is the lower limit, and suppose the corresponding x coordinate of the particle at time 0 was x0. Finally, time is t and the position coordinate becoming x.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.